Welcome back, everyone. Today we're diving into something absolutely incredible. We're going to break down the sheer, complex anatomy of a space mission, literally tracing its path from that very first spark of an idea on a whiteboard all the way to its final resting place in the space graveyard. So get comfortable because this explainer is going to take you on a massive, step-by-step journey through the life cycle of spacecraft engineering. Let's get right into it.
Okay, before we jump into the deep end of rocket science, let's just anchor ourselves with a really quick foundational definition. What actually is a space mission? Well, it's a planned operation in which a spacecraft is launched to accomplish one or more specific objectives in space. Now, I know that might sound super straightforward, but the key takeaway here is that every single mission, no matter how small or unbelievably massive, starts with a clearly defined goal. That objective is basically the mission's North Star. It dictates absolutely everything, from what orbit we choose to the type of rocket we need, right down to the battery size. Everything stems from that one initial goal.
So here is our flight plan for this explainer. 1. Why we go to space. 2. Designing a space mission. 3. Liftoff and daily operations. And 4. The space graveyard.
All right, part 1. Why we go to space.
You really have to ask, why do we spend billions of dollars and years of our lives to shoot things into the harshest environment imaginable? Well, in space, form perfectly follows function. If your objective is communication, say you want a satellite to beam TV, phone signals, or internet over one huge fixed area on Earth, you absolutely need continuous coverage. So you have to park it in GEO, or geostationary Earth orbit. But if your goal is Earth observation, like monitoring crops or studying the climate, you need super high-resolution pictures. To get those, you've got to fly much closer to the planet, right? That means you're operating in LEO, low Earth orbit. And for navigation, think of the GPS in your phone, you actually need a middle ground. So those satellites hang out in MEO, medium Earth orbit. But hey, the scope of what we do up there goes way beyond just internet and GPS. We've got scientific research missions where we're launching probes to touch the sun or chase down comets. We have national security missions which rely on some seriously classified payloads for surveillance and missile warning. And then, of course, there's human spaceflight. Now, putting humans in space, that drastically shifts the entire paradigm. The literal second a human crew is involved, the engineering challenges just multiply exponentially. You suddenly need massively complex life support, environmental controls, escape systems, and yeah, you have to figure out how to build a reliable zero-gravity toilet.
Moving right along to part 2, designing a space mission.
So this is where those big, ambitious dreams finally crash into the harsh reality of engineering constraints and budgets. Mission analysis is the absolute foundation linking your initial objectives to the actual design of the spacecraft. It's kind of like planning the ultimate extreme road trip into a total void. You absolutely cannot call a mechanic or a tow truck once you leave the driveway. You have to pack every ounce of fuel, all your power systems, and your hardware perfectly. This analysis is that painstaking starting point where engineers crunch the numbers on mission duration, payload needs, and budget to optimize everything and eliminate as much risk as humanly possible before a single bolt is even turned. Check out this timeline. It really shows the relentless, structured momentum of a space mission. It doesn't just happen overnight. Look at year -5, mission concept. Engineers are literally just trying to see if the idea is technically feasible and if they can actually afford it. Fast forward to year -3, mission design. This is where they lock in the orbit, the spacecraft architecture, and the launch vehicle. Then, year -1, development and testing. The pace gets crazy here as hardware is actually built. And then, the tension completely spikes at day 0, launch. From there, assuming that all goes well, the heartbeat kind of slows back down as we enter the operational phase, which can last anywhere from a few months to well over 15 years, before eventually reaching end-of-life disposal. It's a staggering, multi-decade commitment.
Now, I want to hover on that year -1 testing phase for a second, because like we said, you can't exactly send a repair person to orbit. These qualification tests are absolutely brutal, and they are mandatory. Engineers will subject the hardware to insane vibration and acoustic tests just to make sure the spacecraft won't literally shake itself to pieces from the sheer violence of riding a rocket. Then they throw it into thermal vacuum chambers to mimic the extreme freezing and boiling temperatures of space. They also run electromagnetic compatibility, or EMC tests, to guarantee that the onboard computers don't just short out or scramble each other's signals. It literally has to survive hell before it even gets to the launch pad.
Let's put this into perspective and contrast two totally different extremes, just to see how these early constraints dictate a mission's DNA. On one side, you have a simple Earth observation satellite. It's relatively low budget, it's a smaller mass, and it's taking a pretty standard path to low Earth orbit. Simple, right? But on the other side, look at human spaceflight. The budget is astronomically high. The demand for extreme redundancy and reliability, completely non-negotiable. And you are carrying an incredibly heavy life support payload. The choices engineers make during that early mission analysis entirely dictate which of these drastically different paths the mission will take.
Okay, Part 3. Liftoff and daily operations. Years, literally years of meticulous planning all come down to this exact moment. Welcome to the launch and early orbit phase. Engineers affectionately, and maybe a little fearfully, call this LEOP. The countdown hits 0, the engines light up, and all that theoretical math is put to the ultimate physical test. The spacecraft separates from the rocket, and suddenly it's completely on its own in the dark. It has to execute this nail-biting checklist automatically. Step 1, deploys solar panels. If it doesn't get power immediately, the mission is over today. Step 2, deploy antennas. Step 3, perform initial system checks to make sure nothing snapped during the launch. And Step 4, establish ground communication. Imagine the dead silence in mission control waiting for that first ping. That one single connection basically dictates if a multi-million-dollar asset is alive or dead on arrival.
Whew. Okay, so once that signal is locked in and the sheer terror of LEOP finally subsides, the spacecraft settles into its operational phase. The dramatic, chaotic launch is in the rearview mirror, and now begins the daily, relentless grind that this machine was meticulously built for, whether that's for a few months or for well over 15 years.
So, what does a spacecraft actually do all day? Well, it is highly choreographed. You have continuous payload operation and data collection. You have orbit maintenance, which means firing tiny thrusters every now and then just to keep the satellite exactly in its designated lane. There's attitude control, making sure the solar panels are always catching the sun and the cameras are pointing at the right target. And of course, constant communication with ground stations back on Earth. And I really want to emphasize this for you. Every single time you check a weather map, or route your drive on your phone, or watch a live international broadcast, you are directly personally benefiting from these flawlessly executed space operations.
Which brings us to our final section, Part 4, the Space Graveyard.
So we've dreamed it up, built it, launched it, and operated it for a decade. But here's a question for you. What actually happens to a billion-dollar satellite when it finally runs out of gas? You can't just leave a dead hunk of metal flying around at 17,000 miles an hour. Responsible retirement is a hugely vital aspect of this whole process to stop the buildup of dangerous space debris. Engineers actually plan for end-of-life disposal on day 1. For lower orbits, they do a controlled atmospheric re-entry, letting the spacecraft safely burn up in Earth's atmosphere. For higher orbits where that isn't possible, they actually push it out into a graveyard orbit, essentially moving it safely out of the busy operational lanes. They also do passive deactivation, venting leftover fuel and draining batteries so it doesn't accidentally explode later. And for deep space exploration missions, sometimes they literally plan a controlled planetary impact. Proper disposal is absolutely non-negotiable for the future of spaceflight.
And that really leaves us with one massive lingering question. As space becomes more and more crowded, how will we ensure the long-term sustainability of our cosmic footprint? We've just traced the incredibly complex anatomy of a space mission, from a drawing board concept all the way to its final resting place. But with new satellites launching practically every week now, managing our orbital environment is definitely the next great engineering challenge of our time. We can't just design for the mission anymore. We have to design for what comes after. Thanks so much for joining me on this explainer today. Keep questioning, keep learning, and I will catch you on the next one.